Okay, so now we move on to our third and last module, and now we're going to talk about all the challenges that no matter what kind of data you use, no matter what kind of methods you're going to use, if you're doing spatial analysis, you're going to run into those issues, but there are ways to try to overcome or mitigate some of them. And then we're going to conclude with, a few tips on the different software available to be able to run those methodologies. So when we talk about problems, the very first one, it's probably the most discussed one, is what we call the MAUP problem. So the modifiable area unit problem. What is that? The issue around MAUP is that whatever analysis you are doing, it depends on the level of aggregation. So people can have exactly the same data set. They're doing exactly the same technique. But if they work at different levels of aggregation, they're going to get different results. None of them is wrong. But it all depends on what's the right level of aggregation for the question you want to answer. MAUP problem has basically two components. One is what we call the scale effect, which is sort of an aggregation problem. And here, think about an example that we have the same data, but I'm working at the census tract level and you're working at the county level. We're going to get different results. That's the aggregation problem. It's how we change the scale of the data from very detailed to very coarse. The second issue is what we call the zoning effect. And this is sort of the grouping problem. So consider the same level of scale. The issue here is how you rearrange the units that you have at that level of scale, forming different zones. And again, depending on how you do the grouping, you're going to end up with different results. So let me try to illustrate this with this diagram to make this very clear. What we have in here are both the zone and the scale effect together in one diagram. And if you go through the different rows of the diagram, we're basically changing the scale. So we move from a very coarse scale, just a few units in the data, to a very detailed scale with many more units. So this is a regular grid. This is sort of resembling what boundaries of geographical units usually look like. And this is sort of a more artificial way of creating the different spatial units. So this is the scale. Now, if you go over the different columns in here, what we have is, take the first row. Here we have exactly the same scale in the three columns. But in each one, you have a different way of grouping the units at that level of scale. That's the zoning effect. So you're changing the way you group. And as you change the way you group, you can also get different results. Now, let's try to illustrate this with some numbers. Here's a very simple one that basically shows you how mapping a certain indicator can show a completely different reality depending on how you deal with scale and zoning. So the two diagrams on the top are basically the denominator and the numerator of the indicator. So you want to get the percentage of people that get a university degree, okay? So if you look in here on the second row on the left, this is the diagram showing, or let's say this is the map showing the indicator for the units you had in the beginning. So you have 9 spatial units in here, and the percentage goes from 5% to 25%. Now let's change the scale. Instead of having 9 units, you're going to have only 3. So you moved from a detail to a much coarser scale. Now instead of ranging from 2 to 25, now you range from 6 to 9%. So think about describing this particular indicator in the map. Completely changed the story by changing the scale. Now here what you have is you still have 3 units, so the scale is the same, but we're going to change the way we group those 3 units in a space. So we're dealing with the zoning. So here's what happens. It goes from 7 to 10 and from 4 to 16. So all those 3 diagrams here that have 3 units, they describe 3 completely different stories, and they're all based on the same data. So again, the scale and the zoning effect. Now, it's not just the indicator that is different, but if you start looking at statistical measures related to that data, they're also very different. So take only two, the average and the variance. And on the top row in here, we see the effect of scale in this data. So we're moving from having 16 spatial units, and we aggregate to only 8, and then to 4. Now, in this particular example, which is hypothetical, the average remains the same in the entire process. But look at what happens with the variance. It goes from 2.6 to 0. So you move from one reality, one context, where there is a very high variance, to one where the variance is 0. So basically, the message here is by reducing the scale of your data, which means making it more coarse, you remove the variability that you had when you had fewer spatial units. A similar story when you change the zoning. So here, those two, both of them have 4 units, 4 spatial units, so they have the same scale. But look at the variance. One is 1.04, the other one is 2.11. So not only you are showing a map that has a different mapped outcome, but it also has different measures of dispersion associated to it. The classical example that describes MAUP is from Openshaw and Taylor. It was published in '79. And here's the exercise. Take one state in the US, Iowa. It has 99 counties. And the question that is being asked is, what's the correlation between population over 65 and people registered as Republicans? Very simple question, pretty straightforward data, okay? So when they do this, when you calculate this correlation for the 99 counties in Iowa, you get a correlation of positive 0.35. Great. So here comes the exercise. Let's change both the scale and the zoning. And the first attempt was to change from 99 counties to only 48. So you're changing the scale. But try to rearrange this 48 in many different groupings. So now you're changing the zone, okay? So you're changing both at the same time. What we get is that the correlation now is gonna vary from negative 0.55 to positive 0.89. So it can be anything. Let's keep going. And now instead of the 99 counties, we're gonna have only 12. And again, we're gonna rearrange those 12 in many different types of zoning, in many different types of grouping. What is the result? Now the result basically tells you the correlation can be anything from minus 0.94 to 0.99. So basically you can take those results and say there is a huge correlation between elderly and being a Republican. There's absolutely no correlation between being elderly and a Republican. Now, you probably can start feeling what is the key issue with the MAUP problem, is that for people that don't have good intentions, you can manipulate the data to show the results you want and not account at all for the fact that the spatial analysis that is being done can have a problem of scale and zoning. Now, one of the key issues when you talk about zoning is how you define voting districts. There is a huge literature on this, not only in the US, discussing how you define those voting districts. Why? Defining voting districts is a matter of both scale, but mainly about zoning. And the way you group units to form those voting districts can change an election. And here is a very hypothetical example where you have two parties, a red and a blue. And originally you had 9 voting zones and you had 1,420 voters in those 9 zones. So here what you do is, in this configuration, the reds would win 5-4. If you start changing the scale, then you can have the reds still winning, but by a smaller margin. You can have a tie, and now you can reach a situation where the blues are going to win instead of the reds. So again, that's another example. that in this case related to elections, how you change the scale and you reorganize the units can determine who is going to win the election. Now, it's a big problem. We saw several examples. What do you do about that? We don't have a recipe on how you address this. We don't have a clear-cut answer on how you address this. What we have is a lot of strategies to be able to handle the problem. And one of the main ones is you have to recognize that this is an issue and make it right clear from the beginning that it is an issue and show the impacts that that can have. Most importantly, you cannot start making inferences at the individual level if you're actually analyzing aggregated data. You have to be very clear, very aware of what's the aerial unit you're working with. What's the aerial unit it matters for your research question. I'll say this again because you have to be aware of what is the aerial unit for your research question. So if you are evaluating an intervention and the intervention only makes sense to be evaluated at the district level, you cannot do an analysis at the village level or at the municipality level. So you have to do the analysis at the unit, at the aerial unit that makes sense based on your question. The other thing is, in recognizing the problem, you have to do a multi-scale analysis and show the difference it makes. You recognize the issue and you show the impacts, but then you go back to your research question and then you show the results. And the last thing you can do is you can play with the different zones as well. And there is a procedure that is pretty common now that is called automated zoning procedure that allows you to optimize the zoning and again show the impacts that that can have in the results. So the key message about the mouth problem is it's always going to be there, no matter the data you have. It is going to be there. And the best strategy is to be aware of it and recognize the fact that the issue happens and then be very clear and transparent in the results. The second issue I want to talk about is what we call edge effects. So unless you're working in an island and at the edge, what you have is just water, you're always going to have the edge effect. What does that mean? Look at the diagram on the left in here. So let's assume this is your study area and that those dots are the points that you observe on the ground. So whatever data you're collecting. Now, if you take those points here right at the edge, whatever you observe for those points, and you want to create a neighborhood for those points, you don't have neighborhoods on this side because it's on the other side of your study area and you don't have data for that. What is the key problem? So if you're defining a neighborhood to be able to see if you have spatial effects, if you look at the points at the edge, you don't have enough neighbors. You don't know what happens across the boundary of your study area. Now, it doesn't mean that there's nobody there. So let's say if you're looking at dengue, right? There are dengue cases on the other side of the boundary of your area. You just don't observe them. You don't have data for them. What it means is that when you do any kind of analysis at the edge, the results are probably going to be biased. They're probably going to be compromised because the relationships are different in there. You cannot measure the entire neighborhood for those points. What's the solution then? Well, there are different things you can try to do. If you can collect more data, change your sampling, you can actually get data surrounding your study area that you're not going to analyze in the sense of showing any kind of results for those points, but you're going to use those points to form the neighborhood that would allow those points at the edge to have results that are much more robust. If you cannot do that, then, and if you have enough observations to give away some of them, you can create sort of a guard area, and here is represented by this dotted red line. So basically what you do is what is inside this red area becomes your study area, your new study area. You're not going to report any results for this edge area here, but you're going to use the points in the edge area to be able to create very good neighborhood structure for the points in the new edge. So you basically use your own data to give more strength to the analysis that you're doing. Again, not always you can do this, because if you have a very small sample, you don't have the luxury of giving up some of your observations to improve the robustness of what you do inside that area. Now, whatever data set you're using, usually you have missing data. It's no different in spatial analysis. However, one question you need to ask whenever you think you have missing data in spatial analysis is this real missing? In other words, what's the nature of what you think is a missing data? Why is this? Take your study area, or think about the map that I showed to you on the second module, the map of Africa, that had a hole in the middle showing no schistosoma. That was the DRC. Well, in that case, it's real missing, because nobody collected information on the schistosoma type in that particular area. Let's say you look at your study area and there is a whole stripe of land, there's absolutely no data. Well, maybe there's no missing data there. Maybe it's a large river or a mountain range and nobody should be living in there. So some of what may look like missing data could be a physical feature of the landscape that shouldn't have data in the first place. Another situation is when you have restrictions to access the data, and therefore you cannot map them, and therefore they look like missing. Another thing is when you have real missing. So the data wasn't collected by the interviewer, or for whatever reason the data didn't enter your database. So that would be a real missing that you have to deal with. But the key message here is that usually when you're working in space, you don't have empty areas. You can have features, you can have challenges of confidentiality, but you don't have an area that naturally should be empty without any kind of process happening there. Now, the way you handle missing data is very similar to the way you handle missing data in a regular data set that doesn't have spatial variables. You can do data imputation. But here, you can do spatial interpolations, or even better, you can do spatial estimation, as we saw in Module 2. And this can be extremely useful because you borrow information from the locations that you do observe data, and then can come up with an estimation for the points you don't observe. So again, if you do have missing data, one, what's the nature of the missing? Is it really real missing? And two, if it is, there are ways to be able to address missing data if the percentage of missing is really high. Now, a very important issue, and I mentioned this a few times before, is confidentiality. So whenever you're doing a study, you need an IRB approval. You need to guarantee that the privacy of your subjects is guaranteed, okay? Well, in spatial analysis is no different. But it has sort of an additional layer of complexity, because here it's not only about finding the characteristics of a person that would allow you to identify. You can identify the house where that person lives. And that can really violate confidentiality issues. Now, why does that happen? One of the reasons is we still do a very poor job in coming up with guidelines on how one should release spatial data, share spatial data, publish spatial data. So if you want to share data, there are ways that you can adopt to de-identify the data spatially. So you can remove some of the variables, you can aggregate variables, you can shift point locations, and that's what the demographic health survey does. They take the locations of the clusters, the survey clusters, and they displace those clusters. So any DHS data that has clusters, they're displaced, all of them. So there are ways that you can try to address this issue of confidentiality before you actually make the data public available. Now, another issue that is of concern is, so sometimes you do a really good job in guaranteeing the confidentiality in your data, but somebody can download a data set that is publicly available somewhere and link this data with your data and then be able to identify people. And this is quite common today, more common than we can think about. I mean, there are tons of data sets that are available online that you can start linking with survey data, census data, or link among those data sets and be able to identify lots of characteristics of people. So a few issues here is sometimes you can publish data that you think is completely harmless. But if you have points, another person can come, digitize that data, and do what we call reverse identification. And I'll show an example in a minute. The problem is those things are happening because there's still a long way to go in making journal editors and reviewers more aware of what should get published and in what resolution. We also have to do a much better job in providing guidelines to researchers so they know what they should be publishing in a map or what they should just report as results. And above all, we have to sensitize the media. There are tons of maps that are published every day in newspapers that shouldn't be there because somebody can come, digitize those maps, do a reverse identification, and find out where people live. And here, just to make the point, is one example. The map on the left was published in a peer-reviewed journal, and this is Boston, and the red dots are locations of patients extracted from medical records in a hospital, okay? So the map was published. As you can see, there are no roads, there are no streets, there are no references other than the boundary of Boston and the points. So somebody digitized this map, combined those points with a layer that has all the streets in Boston and all the compounds in Boston. So you have every single building. And that's the map on the right side. And there is a zoomed area. And what you see in this insert in here are these red circles are the location of the plots as originally published in the paper. And the blue polygons are the houses. And the identification was extremely high. So you take this map that was published in a journal, and the researcher and the editors thought it was completely harmless. You digitize this map, and now you know the exact address of each one of those patients. So that's one example there. There's another interesting example, which is a map that was published in a newspaper showing the destruction of houses after Hurricane Katrina. And again, somebody took this map, digitized, combined with additional data, and was able to identify all the residents in those houses. What seemed like a harmless map, very informative for a newspaper, generated a lot of fuzz after it was done because names of people could be listed for each one of the houses identified as damaged. So if we try to summarize sort of the bad news, and I don't quite consider this to be bad news, but the main one is a lot of the data that we use to look at social determinants of health is going to be spatially dependent. So there's going to be some spatial correlation in there. I don't think this is a real problem, and we're going to talk about this in a moment, but it's actually to your advantage to be able to better understand the processes that you're trying to measure. And obviously the second issue is whatever you're trying to do spatially, it's going to be dependent on the scale you're using, the zoning you're using, the sample size that you have, so if you have enough data to deal with edge effects. But again, if that's bad news, I guess the good news is we can handle all of that. So we have strategies to be able to either completely overcome those problems or mitigate some of those problems. And I really think that if you do have data with spatial effects, that actually makes your work much better because you probably can get a much better and deeper understanding of the processes leading to a particular health outcome. And above all, you can use this knowledge to make a much more informed decision regarding policymaking. And you can, going back to the very first quote I showed you on Module 1, you can design policies that are targeted to individuals but it's also targeted to places where those individuals are. So now I want to say just a few words about software. The list is long. Some of it is free, which is great. Some of it you have to pay a lot, which is not so great. But I guess the good news is you can do a lot with free software, so you really don't have to spend tons of money to be able to apply those techniques. Again, I give you a link on the top of the slide that has a huge list of all the available software. It says if it's free or not, and it says what it does. So what kind of techniques you can apply using that particular software. I want to highlight 3 of them. And with those 3, you can pretty much do everything you need. You can do everything we discussed in here. The first one is R. And R is a free software, it's a statistical package. It requires programming, but the good thing is we have a whole set of libraries that have been prepared already to do spatial analysis. So there's not a lot of programming you are going to have to do yourself. You can just download those libraries that are very well documented and then apply those methods in your data. The second one is Geoda. It's also free and do all kinds of spatial exploratory analysis. It does clustering and it does spatial regression when your goal is to add lag terms in the regression model. And the last one is SATScan. It was written by a professor here at the Harvard Medical School. It does cluster analysis, but a very special type of cluster analysis that allows you to bring together space and time in the same framework. So I showed you at least one example when I showed dengue in Vietnam. It was using exactly this method, and it's also free. Now, I just want to close with sort of on a good note in here. So this is a supplement from the Global Health Action Journal that came out in 2010. And in this particular supplement, they had all those different studies that were done looking at clustering of mortality using in-depth data. So I guess what we need is to start seeing more of those supplements. It doesn't have to be only with mortality. We can start addressing other issues on health-related research, but most importantly, you have to start taking advantage of the extremely powerful data that you have and accounting for space in that data. Thank you.